Hello and welcome back. So, in this lecture, we are going to look at the first law of thermodynamics, which is also often called as the law of conservation of energy, and we'll see what that is in a moment. So, this dates back to the experiments of Joule, who looked at systems of this kind, which is shown here. So, he had a system which was filled with, say, water, and he had a paddle wheel which was connected to a string, and you had a pulley and you had a mass. So, you can do experiments of this kind where, for example, you let the mass slowly drop, it rotates this paddle wheel and the water inside is churned. And what we know in this kind of a case is that there is a lowering of a mass, therefore, there must be work done on the system, which is shown by this dashed line over here. So, we can calculate how much that work is because we know the distance by which the mass is dropped, and this is a slow process. So, mass moves slowly down and we can calculate the amount of work which is done. So, we call that small amount of work as delta W and del W, and we can integrate this from the initial to the final state. So, when we do this kind of experiment, so the water over here inside this will be churned by this fan and the temperature of the water will rise. So, what Joule did is he did experiments of this kind and then waited for the water to dissipate heat and come back to its original temperature. So, he measured the quantity of work which is done and measured the quantity of heat which is transferred afterwards through these walls. So, we have some heat transfer, you can measure it using a calorimeter. We have work because of this mass being moved downwards. So, for this system, work is being done on the system. So, there is work going in through this shaft, we can calculate that as well. And whenever this experiment was done, so initially we have some state here, we have some temperature, the water is at rest. After this experiment completes, after this mass drops, after some time heat is dissipated, once again we find that the temperature after a long time is the same as it was initially and the water is once again at rest. So, what we see is that this is a cyclic experiment or a cyclic process. So, we start at one state and we come back to the same state. So, that kind of process is what we earlier called as a cyclic process. And if you calculate the amount of work done, measure the amount of work done and measure the amount of heat which is transferred, what was found is that they were proportionate. The quantity of work done and quantity of heat transferred were both proportionate. Joule, of course, was using different units for heat and different units for work. So, today we use SI units, and in SI units what we see is that if you find out the cyclic integral of the work done, which is you calculate the work done during this entire process, and the cyclic integral of the heat transferred, which is the heat transferred in the entire process, we find that this is equal when using SI units. So, what we see is that if you use other units, you have some proportionality constant, which is often called as the mechanical equivalent of heat, which has a value of 4.2. Maybe when you have one of them in joules and the other in calories, but we are going to restrict ourselves to SI units, and in this case what we find is that you get this kind of an expression. So, the amount of work which is transferred in this process, in the cyclic process, and the amount of heat which is transferred in the cyclic process are equal once you come back to the original state. So, this is our expression of the first law of thermodynamics for a cyclic process. We see that the cyclic integral of the work done is equal to the cyclic integral of the heat which is transferred. When this experiment is done in different configurations, in all the configurations in which people have tried this out, we always find that this is equal. There is no proof of this law. All we can say is that we have tried to find cases where this does not hold. So far, nobody has been able to find a case where this is not true. So, in all the processes we have seen, this first law holds good, and this is what we call as the first law of thermodynamics for a cyclic process. So, we can look at what happens in non-cyclic processes as well. So, let us say we have some kind of a system we go from some state 1 to some state 2 along some path. We come back from state 2 to state 1. This would be a cyclic process. So, we can go along some path A and we come back along some path B. So, what the first law says is that the cyclic integral of del W is equal to the cyclic integral of del Q. This cycle we can split it into processes. So, if we are doing that, we can also write it in this form. Where we are looking at each of the processes separately. So, we can separate this out as, for example, the work done in going from 1 to 2 along path A plus the work done going from 2 to 1 along path B is equal to the heat transferred going from 1 to 2 along path A plus the heat transferred going from 2 to 1 along path B. So, this is another expression which gives the essentially the same first law for this process, where we have two distinct processes by which we go one along A from 1 to 2 and along B from path state 2 to state 1. So, we see this is another expression of the first law for a cyclic process again. So, what we see now is that supposing we just go from some point 1 to a point 2 and do not come back, then of course, we do not know how to use this yet, because this only tells what happens when you have a cyclic process. It does not say what happens when you do not have a cyclic process. So, what we can also see over here is, if I take the amount of heat transferred along some path A and I subtract it from the work. So, if I just rearrange this a little, so I get the amount of heat transferred along path A going from 1 to 2. I take this to the other side. So, I have this minus the work done going along path A from 1 to 2 is equal to the heat transferred minus of the heat transferred going from 2 to 1 along path B plus the work going from 2 to 1 along path B. So, there is a minus sign here. I am taking the minus outside. So, we get something of this kind. Or I can take this, what I see is the difference in the heat transfer and the work done going from 1 to 2 is equal to minus of the heat transferred and the work done going from 2 to 1. So, I see something of this kind. So, what I can do is I can call this difference as some difference in some other quantity, which is what I am going to do. But before I do that, what I want to know is this other quantity which I get, is it also dependent on the path, or whether it is dependent only on the states, and we are going to see whether we can show that. So, let us say I go from some point 1 to 2 along a path A and come back along a path B from 2 to 1. This completes a cyclic process. Now, in addition to this, let us say that I go from point 1 to point 2 along some other path, let me call that at some C, and I come back along the same process B from 2 to 1. So, I can write the first law for both of these cyclic processes. So, for the first cyclic process going from 1 to 2 along A, coming back from 2 to 1 along B, I have this expression, which is what we had written earlier, which I will call as some 1. Now, going along path C and coming back along B, I have a similar expression. So, I have cyclic integral of work, which is going from 1 to 2 along C, plus work going from 2 to 1 along B should be is equal to the heat transferred going from 1 to 2 along C plus the heat transferred going from 2 to 1 along B. Because the first law is valid, when I go along C and come back along B. It's also valid when I go along A and come back along B, because both of them are cyclic processes. So the first law must be valid. So what I can do now is subtract equations 1 and 2. And if I do that, what I see is these two terms get cancelled out. So what I am left with is I am subtracting these out. So this also gets cancelled out. So I am just going to rearrange it a little bit. I am going to take this to the other side and this to the other side, or maybe I will take this here. So I get this minus this, and I am going to take this to the other side. So what I get is that the difference between the heat transfer and the work done whether if I go from a state 1 to a state 2, the difference between the heat transfer and the work done is the same whether I went this is B, whether I went along path A or along path C. So that is quite interesting. So I know that heat transfer and work done are both path functions. They depend on the path in which I go from one point to another. But if I take the difference of these two path functions, what it shows is that whether I went along path A or along path C, the difference is the same. And A and C are two arbitrarily chosen paths. So which means that this would be the same even if I went along any other path, say some D or E or F. If I went from point 1 to point 2, the difference between the heat transferred and the work done would be the same. Whenever we have the difference with some quantity whose difference between 2 points depends only on the 2 points where we are, so we know that those are properties, which means that the difference is essentially a property. So that property is what we call as the difference over here is what we call as some change in some other property, some quantity, which we call as energy. Of course, we have to see what this energy is, but essentially what we see is if you go from some state to another, there is something which changes. It does not depend on how you go, as long as you start at the same point and reach at the same point, the difference is the same, and the difference in that quantity is the difference in energy. Or in differential form, what we can say is a small amount of heat del Q minus small amount of work done del W is equal to the differential energy, or the small amount of change, infinitesimal amount of change in energy. So this is an expression of the first law for a process, any process. So we had the first law for a cyclic process where we had the cyclic integral of del Q is equal to the cyclic integral of del W. For any process, we see that del Q minus del W is dE. We of course know that if you, for a property, if you go from one point and come back to the same point, then the change in the property is 0. So if you do a cyclic process, this term essentially becomes 0 and we are left with whatever we had earlier, that del Q is equal to del W when you integrate over the entire cycle. So the first law thus gives us some quantity which we call as the energy. So what it tells us is that if I can find out the heat transferred and the work done, I can find out the change in energy. It does not tell me what is the absolute energy, it tells me I can find out the change in energy when I have something of this kind. This energy is something which we can now split into other forms as well. So, if they have an object which is moving, it has some velocity, we talk of it having kinetic energy. Okay. If we have an object which is on some surface and it is raised, we talk of it having potential energy, and so on. So, we can now split this energy into various forms. So, what we generally do is we say that this energy consists of potential energy and kinetic energy and other forms of energy, which we usually lump together as what we call as internal energy, which we usually denote by the letter U. So, the change in energy dE would be the change in potential energy plus the change in kinetic energy plus the change in internal energy. And energy is an extensive property. It has the same units as work and heat. So, it has the units of joules, and we can also look at the specific property, which will be the specific energy, which will have the units of joules per kg. Similarly, we can look at specific potential energy and specific kinetic energy and specific internal energy. So, if we have an object which is at rest, and let us say it starts moving and it gets some velocity of v, then we would say that its kinetic energy has changed. If it is moving on a horizontal surface, there is no change in its height and it is moving, and there is no change in anything else, it is just moving along, we would say that its kinetic energy has changed. So, in such a case, what we would say is that if you push the object, you are doing work on it, and by doing work you are increasing its kinetic energy and you are trying to make it move faster. So, that is something which we see. So, in that kind of a case, there is no heat transfer. So, if you look at this first law over here, the heat transfer is 0 and any change in energy would be negative of work done. So, we are doing work on the system by moving some block and making it go forward. So, we are pushing it and it is moving on a horizontal surface. So, we are doing work, and that would be equal to the change in energy. But we also know that the work done is the mass into the acceleration. So, we can also try to calculate an expression for that. So, we have a fixed mass, we are looking at a system. So, the mass is not changing, and the acceleration is essentially the change in velocity with respect to time. Let me maybe use something of this kind so that we do not confuse it with volume. So, I also want dx, right. So, I get so this term here is essentially velocity. So, I get an expression of this form. So, if I want to find out the change in energy during this process when this object goes from rest to velocity of v, what I can do is I can integrate. So, I know that minus del w is dE. So, now I can integrate this from 0 to a velocity of v, and I can find out the kind of change in kinetic energy. So, I am going to integrate this. So, the mass is constant. So, I get m, and if I integrate this, I get integrating from 0 to v, I get something of this kind. So, I see that the kinetic energy has changed for this object. It was 0 when it was at rest. On moving it, it now goes to mv square by 2. So, in a similar fashion, I can find out what is the energy when an object is lifted. So, let us say I have the first law again, which is given as in this fashion. Over here earlier what I see is that minus del W is dE, and there is only the change in kinetic energy. So, I can also write this as this form. Now, I am going to take a case where I have an object which is being raised at a constant velocity. There is no change in the temperature of this object, there is no heat transfer. So, this term goes to 0. There is no change in the velocity, therefore, there is no change in kinetic energy, and there is no change in anything else, there is no change in internal energy. Therefore, any change because of work done is equal to a change in the potential energy of this object. So, I have this object, let us say it is sitting on some datum point, I am raising it at constant velocity. So, the work done is given by the force into the displacement. Let us say I move it by a distance of x from some datum plane, okay, which is this plane. So, the work done, and the work done is negative for this object because it is being lifted. So, what I get is that the force is given by mg, and the distance it moved in a small amount of distance moved is dx. So, if I want to find out the total work done, I would integrate this, and this would be equal to the change in potential energy. So, if I want to find out the total potential energy, that is the integral of P going from a height of some reference height, which I am calling as 0, to some height of x. So, that will be integral of mg dx going from 0 to x, which is essentially mg into x. Of course, more commonly we would call this height as some h. So, I would write this as, let us say, going from mg to some height of. So, what I see is that the potential energy change is mg into h, where h is the height by which this object has been lifted. So, I have expressions for the change in kinetic energy when I have an object going from a velocity 0 to a velocity of v bar. I have expression for the change in potential energy when I am going from a height of 0 to a height of h. So, I have expressions of this kind. The internal energy is something else we need to look at. We will look at it again in the context of, say, ideal gases, but essentially what we will say at this point is that it exists because of the interactions between the molecules. The molecules are in motion, they have some amount of energy in the form of vibrational energy, in the form of translational energy, and in the form of rotational energy, because for example, a molecule has 2 atoms. If we think of a molecule as, say, being a dumbbell shaped thing, it can move in this fashion. The atoms can move nearer and apart, they can also rotate, and they can also move. So, whatever energy they have due to the atoms which are there, we will consider that to be the internal energy, and we will look at it in a little more detail when we go on to a discussion of what are called ideal gases. So, what we see now is that we have an expression for the first law for a cyclic process. We also have an expression of the first law for any process. We have expressions for the change in kinetic energy when an object is moving. We have an expression for the change in potential energy when the object is moving, and we can have, if there is no change in kinetic energy or potential energy, then of course the first law in the form which we have gives us the change in internal energy when we do not have any change in kinetic and potential energy. So, this is when these are 0, any change in internal energy is given by this expression over here. So, we can use this form of the first law to do calculations of various processes. So, for example, let us say we have a piston cylinder arrangement. Let us say there is some heat transfer to this, and let us say it is 100 joules of heat transfer to this, and let us say that this piston moves out doing 50 joules of work. Then we can find out what is the change in the internal energy of this system. So, that would be given by del Q minus del W, or in the integrated form this would give us the expression there is no change in the potential energy of the system. There is a horizontal piston here. The center of gravity or center of mass of this piston cylinder arrangement does not change. This system, which consists of this piston and cylinder and the gas inside, is at rest. This cylinder itself is not moving anywhere, so there is no change in kinetic energy. Therefore, any change in the energy of our system must be only due to change in internal energy. So, we can substitute these values. So, over here, for example, there is 100 joules of work. Our convention is that heat entering the system is positive. So, 1 Q2 is positive. We have this piston expanding, moving to the right, which means that this volume is expanding. Our convention is that if the volume expands, then the work done is positive. So, the work system is doing work on its surroundings, and that is positive for us. So, we have minus of the positive value of 1 W2, which is 50 joules, which must be the change in our internal energy, which means that we have a positive change in the internal energy of 50 joules, which essentially tells us that the internal energy of our system has increased from the time it was before the process started to whatever is the value at this point of time. So, what we see is that energy is a property, a extensive property, and we have the corresponding intensive property, which is given by this small alphabet E. In many of our systems, we also come across a combination of internal energy U and pressure and volume. So, this is also a property, as we will show a little later on, and we call it as the capital alphabet H, which is a specific property, and we call this as enthalpy. And corresponding to this value, if you divide all of it by mass, we have this expression, which gives us the specific enthalpy, which is also a property. And we can use both of these in order to solve various problems. And we will look at an example of this as a tutorial problem. Maybe we will upload it separately and we can look at values of those. Thank you.